In this last video cast on the types of colligative properties, we're going to look specifically at osmosis, and we're going to take a look at how we can use the four colligative properties to determine the molecular mass of something that's been changed or something that's been dissolved in a solvent. We'll begin on page 553 of your textbook, where it talks about osmosis. And it says certain materials, including many membranes in biological systems, hey, here's a link between chemistry and biology, and synthetic substances such as cellophane are semi-permeable. When in contact with the solution, they allow some molecules to pass through the network of tiny pores, but not other molecules. Most important, they generally allow small solvent molecules, such as water, to pass through, but block larger solute molecules or ions. This selectivity gives rise to some interesting and important properties. The process that's the most interesting in this area is called osmosis, which is the net movement of solvent, and it's always towards the solution with the higher solute concentration. It's always towards the solution with the higher solute concentration. So it's as if the solvent is moving, so it can, dilute, the solution that's the most concentrated. Well, osmotic pressure actually has a calculation associated with it too. Osmotic pressure is symbolized by the Greek letter pi, and it's equal to capital M, R, T. Capital M stands for molarity, okay, molarity, which is moles divided by liters. R, which is the universal gas constant, and generally it's given in atmosphere, so you use 0.08206. And then this is the Kelvin temperature, of course, as well, okay? So you can see osmotic pressure of a solution is directly proportional to its temperature, and it's also directly proportional to its concentration. Osmotic pressure is measured in units of pressure, which generally are things like atmospheres. Let's take a look at your sample problems page. Let's look at your sample problems page and take a look towards the bottom of the first page, where there's a question number 6 and question number 7. And just a tiny bit more background now, before we actually answer these questions. In number 6, it says of 2 kBr solutions, one 0.5 mol al and the other 0.2 mol al, which is hypotonic with respect to one another. Well, since osmotic pressure occurs because there's a difference in the amount of solute and solvent interaction, there's a difference in the concentration of the solute in different solutions, you use some specific names to call these solutions different things. As a matter of fact, there's 3 terms to describe these. The first is isotonic. Isotonic means that the concentration of the 2 solutions that you're comparing or are separated by a semi-permeable membrane are equal to each other. An isotonic solution, okay? Second of all, if there's a solution that is of low concentration with respect to one that has a higher concentration, okay, we say that the one that is a low concentration is hypotonic with respect to that higher concentration. And then lastly, if we have one that's of a high concentration with respect to one that is of a lower concentration, we say that the high concentration solution right here is hypertonic. Okay, you probably heard as a youngster, something that is hyper is like over and above. Well, something with a high concentration is hypertonic versus something that's a lower concentration. So if you look at number 6 now, and you solve this problem a little bit quicker, knowing those definitions, one of them is 0.5 mol al, and the other one is 0.2 mol al. And it asks which one is hypotonic with respect to the other. Well, hypotonic, remember, describes the solution that's lower concentration versus the other. So we'd have to say that the solution that is 0.2 molal would be hypotonic with respect to the 0.5 molal solution. Okay? So that's the terms. Isotonic, hypotonic, and hypertonic. Number 6 kind of helps you keep those straight. Number 7 says the average osmotic pressure of blood is 7.7 atmospheres at 25 degrees Celsius. What concentration of glucose would be isotonic with blood? So now what we want to find is a concentration, and this goes back to using our equation that we just learned for osmotic pressure. Osmotic pressure, remember, is pi. Okay, that's symbolized by the Greek letter pi. It's not 3.14. It's just symbolized by the letter pi, from the Greek letter pi. Is equal to mRT. And it asks what concentration. So if we're looking for concentration, we're going to be looking for molarity in this case, because molarity gives us concentration. It tells us that the osmotic pressure is 7.7 atmospheres. So we can put that in for pi, or for our osmotic pressure. We're going to solve for m, right? Which is our molarity. Our R is going to be in atmospheres, so 0.08206 liters times atmospheres per mole times Kelvin. And then lastly, we've got to know our temperature, and it says it's at 25 degrees Celsius. And if we change that, it'll be 298. Remember, it's got to be in Kelvin. 298 Kelvin. So solving now for molality, dividing both sides by these numbers right here and canceling, we end up with a molarity equal to 7.7 divided by 0.08206 times our 298. If you do that on your calculator, I believe you end up with a 0.31 molar solution that would be isotonic with blood. Okay, isotonic with blood. Okay, turn the paper over and let's take a look at one last result of these colligative properties that can be really helpful and useful in the lab. And this is using our boiling point elevation, freezing point depression, osmotic pressure, and vapor pressure lowering to determine something called the molar mass of a substance. Okay, if you don't remember what molar mass, remember, is what you look up on the periodic table for something. It's how many grams there are, or mass there is, per mole of a substance. And you can actually take and put this into a triangle where molar mass is equal to our grams per mole. Generally, mass is given in grams because we're the metric system people here. Okay, grams per mole. Now, if you read this problem on the back, we can actually use, in this case, freezing point depression to determine the molecular mass of a substance that's dissolved in something else. It says camphor melts at 179 Celsius, has a particularly large freezing point depression constant of 40 degrees Celsius per mole. When 0.186 grams of an organic substance that has an unknown molar mass dissolved in 22.01 grams of the liquid camphor, the freezing point of the mixture is found to be 176.7 degrees Celsius. What is the molar mass of the solute? Now, the solute is this unknown organic substance right here. It's unknown organic substance. And if we want to know the molar mass, we got to know two things. You got to know the mass, and you got to know the moles. Well, looking back in the question, guess what they give us? They already give us the mass right here. We know 0.186 grams of it is dissolved. So we have half of the problem solved already. The tricky part is finding out how many moles of this stuff are dissolved in here. But since we know how much the freezing point has been depressed, we can use the equation for freezing point depression to determine how many moles of this stuff have been dissolved. Freezing point depression equation is delta T, sub F for change in freezing point, is equal to Kf times molality. And maybe you remember there used to be a little I right here in this equation, which is true, there is, but it turns out that camphor right here, the thing that we're dissolving stuff in, is a molecular substance. And so what's I going to be for that? It's just going to be 1. You're correct. Thank you for saying that. Okay. The Kf is the freezing point depression constant, which is 40 degrees Celsius per mole. We're given that right up here in the equation, or in the question as well. And we can calculate the change in the freezing point, or the freezing point depression, by taking our 179.8 and subtracting from that the depressed value 176.7. So there's a 3.1 degree change, or 3.1 difference in our freezing temperatures. Okay, and this is equal to 1 times our 40, our freezing point depression constant, degrees Celsius per molal. And then we have to remember what molality means. Because remember, our goal is to find the moles, not the molality necessarily. But remember, molality is equal to moles of solute. Hey, that's the thing we need to know right here to find molar mass. Divided by kilograms of solvent. Kilograms of solvent. Okay, let's put that in here. Moles of solute, that's the thing that I want to find, divided by kilograms of our solvent. Well, we're told that it's dissolved in 22.01 grams of the substance. So we can put that right in here. It's dissolved in that much camphor. We just have to convert it to kilograms. So it's dissolved in 0.02201 kilograms of this stuff. And lo and behold, look what we can do. We can solve for the moles of the solute. Since we already know the mass of it from the question, if we find the moles of the solute, we can take grams divided by moles, and we know the molar mass of this unknown thing. What a handy deal. You could do this in the lab, and as a matter of fact, you will. So solving this mathematically, it turns out that if you're going to solve for moles right here, moles end up equaling 3.1 divided by the 40 right here times the 0.02201 right here. And if you end up solving that, the number of moles is 1.705 times 10 to the negative third moles. Sliding this up just a little bit, we can now find the molar mass. The molar mass is our 0.186 grams divided by the moles that we just found right here, which is, 1.705 times 10 to the negative third moles. Our grams per mole now turn out to be approximately 110 grams per mole. That's the molar mass. Remember, when you're using colligative properties, the four colligative properties, boiling point elevation, freezing point depression, osmotic pressure, and the vapor pressure lowering, they depend only on how much of a substance is dissolved in the solution. Not what kind it is, but how much. Can't stress that enough. And of course, osmotic pressure or freezing point depression or boiling point elevation or change in vapor pressure could be used to help you find the molar mass of something as well.